In this final video, we are going to talk about the Doppler shift. It is really useful for us in astronomy, but we can also think about it in sound too. A Doppler shift is the change in the wavelength of a wave resulting from motion of the source and or the observer. Okay, so let's come over here. We've got our stationary source. This works again for sound or light. So here we have a stationary source of sound, since that's what we're talking about right now. And over here is our observer, someone who's watching this all happen or hearing this all happen. We have a sound source here. It's emitting a sound wave. Concentric spherical wave fronts of that sound wave are coming outward away from the center on these concentric shells. So that wave front we can think about as being the crest of that plot of pressure versus distance away from the sound source. So we can think about the crest of that wave being right here at the edge of the sphere. And then the crest of the next wave is out here at the edge of the second sphere, and the crest of the third wave, and so on. And so the distance between the crests of these sound waves, that's what we're calling the wavelength, okay? Now that source of sound, let's say it's a siren on a police car. That source of sound is going to be moving toward you. So the source was here, and then it moved here, and then here, and then here, and then here. And here you are as the observer, okay? So as that source of sound moves toward you, what you experience is a decrease in the wavelength of that sound wave as you're hearing it at your ear, okay? As that source is moving toward you, the wavelength of that sound that you hear in your ear decreases. So if you decrease the wavelength, you increase the frequency. So as that police car is moving toward you, you're going to experience that sound wave as having an increased frequency, a decreased wavelength. We call this a blue shift, and it's more important when we think about light. But we call this a blue shift because when you decrease the wavelength, shorter wavelength waves are actually closer to colors of blue on the electromagnetic spectrum. And so we call that a blue shift. So when the source of sound or light is moving toward us, we call that a blue shift, where the wavelength of light decreases, but the frequency increases. And then if you're over here, you're the observer here, and the source of sound is moving away from you, okay? As that source of sound is moving away from you, whenever you're perceiving that sound, every time that source moves away from you, the wavelength becomes longer and longer and longer between consecutive wave fronts of that sound that's moving away from that source, okay? So as that object is moving away from you, you experience the wavelength of sound getting longer and longer and longer. So when the wavelength of sound gets longer, the frequency decreases. And longer wavelengths, when we think about light in the electromagnetic spectrum, longer wavelengths of light are closer to the red end of the electromagnetic spectrum. So when an object moves away from us, we call that a red shift. The wavelength increases and the frequency decreases. So this is the Doppler effect. And you experience it, you know, with sound when you hear, let's say, an ambulance go past you. When it gets closer to you, you hear the frequency of the sound go up. And when it moves past you and away from you, you hear the frequency of the sound diminish, okay? So that all has to do with the Doppler effect, the Doppler shift. Here's an example of the Doppler shift that we use in astronomy to tell whether stars are moving toward or away from us. Now, so when the objects are moving, the stars moving toward us, the wavelength of light gets shifted more toward the blue. When the star is moving away from us, the wavelength of light gets shifted towards the red. So when the object is moving toward us, we say that it's a blue shift because the wavelength of light gets shorter. And when the star moves away from us, we say that it's red shifted. The wavelength of light gets longer, closer to the red on the electromagnetic spectrum. Of course, there's an equation that goes along with the Doppler shift. Here is an equation that tells us the frequency that the observer hears of the sound if the source is moving and the observer is stationary. So in this example, as a source moves toward or away from you, the frequency you hear is higher or lower respectively. So we already said if they move toward us, the frequency is higher. If they move away from us, their frequency is lower. So here in this equation, we've got the frequency that the observer hears of the sound equals the frequency of the sound wave coming from the source. So if you are standing at the source and you take the frequency of the sound right there without moving, that's the frequency of the source. Now VW here, that's the velocity of the sound. That's the velocity of the sound wave itself. And V sub S here is the velocity of the source, okay? So we said that when an object moves toward us, we experience an increased frequency. How do you get an increased frequency? You get an increased frequency when this bottom number in this fraction is smaller, okay? The top number relatively is bigger, the bottom number is smaller to have an increased frequency. So that means that when the source is moving away from us, we're going to use this equation with the velocity of the sound wave, that's V sub W, minus the velocity of the source. So this is what we'll use. The minus sign is used for motion toward the observer. So if the cop car is coming toward us, we're going to use this equation for the moving source of the sound with a minus sign on the bottom here. Now, if that cop car is moving away from us, the sound we hear from the siren will have a reduced frequency. You can reduce the frequency by increasing the bottom number here on their fraction. So when the object is moving away from you, the object that's creating the sound is moving away from you, you would use the speed of the sound wave itself plus the velocity of the source away from you. So that's why you have the plus or minus here. You use the plus sign when the object is moving away from the observer, and you use the minus sign when the source of the sound is moving toward you. Okay, I know it's a little bit confusing. So this was an example where the observer is stationary, the source is moving, but you could have the source stationary and the observer moving. And in that case, the frequency that the observer would hear, the observer is moving, the source is stationary, would equal the frequency of the source times the speed of the sound wave plus or minus the velocity of the observer toward or away from the source divided by the velocity of the sound wave. Okay, so in this case, we want to use the plus sign for more motion toward the source. So when the observer is moving toward the source, we're going to have a plus sign. And when the observer is moving away from the source, we're going to use the minus sign up here. So anyway, it's all about the relative speeds. So when you think about which equation are you going to use for the Doppler shift, think about, do you have a moving source or do you have a moving observer? You can also have a moving source and a moving observer at the same time, but we won't get to that this time, okay? And then always remember that if the source and the observer get closer to each other, the frequency is going to increase. And if the source and the observer get further away from each other, the frequency is going to decrease. So you look at this equation and say, okay, when I use a plus sign or when I use a minus sign, is the frequency going to increase or decrease in the way that I know it should for the Doppler effect? There's a lot of real life medical applications with the Doppler shift. Okay, in astronomy, we use it to determine whether galaxies are moving toward or away from us. Turns out that our universe is expanding, so all galaxies are moving away from us. We use the Doppler shift looking at light to help us understand that we have an expanding universe. We can also use that to think about the motions of stars toward or away from us in the sky. The Doppler shift also has a lot of medical applications. For example, ultrasound. Ultrasound just means that it emits a sound wave that's higher than the frequency that humans can hear. Okay, so the little ultrasound wand that you rub on the mama's belly or any body part that you're trying to learn more about, it has a speaker and a microphone which detects the sound coming back. Okay, it's all about kind of getting the echo of that sound back, and can use that information in order to figure out how fast things are moving and the density of material. So the ultrasound detects how long it takes for a wave to be reflected back from the tissue and the intensity of the reflection. The intensity of the reflection also tells you something about the density of the materials in the body. Okay, so you can also use the ultrasound to figure out if you've got a mass of tissue that shouldn't be there. Okay, with the Doppler ultrasound, you can also look at frequency shifts in the reflected wave. And with this, if we know information about the frequency shift using the Doppler effect, we know what the frequency of sound is leaving from the receiver. We get a reflected signal back. Getting that reflected signal and looking at the frequency of that reflected wave, we can determine the velocity of the material that wave was moving through. And you can figure out, is the velocity of that material either toward or away from you with the Doppler shift by using those equations that we just saw with the Doppler shift. And this is often used to observe the blood flow in the human body. It's a blood flow in the heart. I've had Doppler ultrasounds before on my heart to learn about the flow of fluid through my valves in my heart. So now we're going to apply the Doppler shift to solve a problem where we think about the frequency of sound coming from an approaching train.
This is a problem about Doppler shift. We have a train that is moving at a speed of 88 miles per hour, which is also 39.3 meters per second. 88, special because of Back to the Future. So this train is moving at 88 miles per hour, and it sounds its whistle, and its whistle has a frequency of 500 hertz. Determine the frequency heard by a stationary observer. This is over here. Frequency of that the observer hears, question mark, as the train approaches the observer. So my observer is stationary. The train is coming toward the observer at a speed of 39.3 meters per second. So in this case, I'm using S to represent the source. So the velocity of the source is 39.3 meters per second toward the observer. The frequency of the source is 50 hertz. So we want to find the frequency of sound that the observer hears, and the temperature is 24 degrees Celsius. So in order to do that, we have to use our equation for the Doppler shift. So the frequency of sound that our observer hears is equal to the frequency that the source emits. So the frequency emitted by the source, if we were sitting right on the source, this is what the frequency is of that whistle, times, we're going to say V, which this V is the speed of sound, plus or minus the velocity of the observer divided by V, plus or minus the velocity of the source. Okay, the plus or minus because this equation satisfies all the possibilities we can have for problems that involve Doppler shift, because you could have 4 different possibilities for the velocity of the observers relative to each other, toward or away, vice versa. Okay, so in this case, our observer is stationary, so their velocity is 0. That helps us out a little bit. But we know that when an object moves toward us, its frequency must increase. The frequency that we hear as the stationary observer must increase. So if V is toward, frequency heard by the observer has to go up. We know that because of the Doppler shift effect. So let's look over here. If the frequency heard by the observer has to go up, in order for that to work, this quantity down here on the bottom has to be reduced. It has to be smaller. And so we are going to use the negative sign here. So we're going to say V minus V source. This is going to be the frequency of the source times V, speed of sound, divided by speed of sound minus the velocity of the source toward the observer. Okay, so then we've got the frequency of our source, which we know is 500 hertz, and then we're going to multiply it by, we got to figure out what is the speed of sound on this day where the temperature is 24 degrees. So we can use our equation for the speed of sound. That speed of sound is 331 meters per second times the square root of the temperature outside divided by 273 Kelvin. Okay, so we've got 331 meters per second times the square root of, this temperature has to be in Kelvin. So we have to do 24 plus 273 Kelvin divided by 273 Kelvin. So then our speed of sound is 345.2 meters per second on a day when the temperature is 24 degrees Celsius. Then on the top of my fraction here, I've got 345.2 meters per second. I'm going to divide it by 345.2 meters per second minus the velocity of my source, which was 40 or 39.3 meters per second. Okay, you'd use 39.3 meters per second. And then that gives us a frequency heard by the observer of 566 hertz. So as the train is moving toward us, the frequency goes up. If our train was moving away from us, instead of minus here, we would use plus. And if our train was moving away from us, so let's say V source opposite direction of motion, then we would hear a frequency of 448 hertz. So if our train is moving away from us, then we hear the frequency decrease. If the train is moving toward us, we hear the frequency increase.